The harmonic motion notation by using a vector traveling rotating about the center also helps to define simple equation for the vibration model. So we have considered that a vector in space having theta degree from the x-axis is rotating with an angular velocity of omega. So this thing, when it is the projection is taken along the y-axis, you get a sine wave. So the sine wave with respect to theta, if you make it analogous to the vibration model, then you have time on x-axis. So if you want to know theta at any time instant, then if the omega is the angular speed of rotation of the vector, so then what will be the value of theta? So theta will be equal to omega t, because omega is the angular velocity in radians per second and t is the time. So at any particular time t, omega into t will give you angular displacement. So if you want to form the equation for this graph, the sinusoidal function, you have x, that is displacement, is equal to x0, that is the amplitude or the radius of the vector x0, sine omega t. So here it is x, this distance is x0 sine theta. So theta is equal to omega t, so you have x0 sine omega t. And now if you are considering a wave which is shifted by some phase, so there is some initial phase there, let's say phi. So initial phase is there, it is not starting from 0, so the x is equal to 0 is not happening at 0 time, it is happening at some instance of uh, time after the 0, t is equal to 0. So this thing is called initial phase or lag of wave in time. So time can be converted to theta with the help of angular frequency. This is the use of angular frequency for that what we have defined. So in that case, x will be equal to x0 sine omega t plus phi. So phi is phase, initial phase. So it is not starting from 0. So any general harmonic wave can be formed by using this equation, by using the property of the circle traveling in the property of the vector traveling in circle. Now this helps us to get the maximum velocity and acceleration very easily. So that's why we have defined this convention. So if you want to get the velocity, that is equal to dx by dt, so you differentiate this expression d by dt of x0 sine omega t plus phi, omega t plus phi. So this will be equal to x0 omega, differentiation of sine theta is cos theta, cos omega t plus phi, and differentiation of this function is omega. So omega will come outside. So the maximum value of cos theta is 1. So maximum velocity of a body in simple harmonic motion is equal to x0 omega, that is amplitude multiplied by angular frequency. So without doing a very detailed derivation, if you know the body is executing simple harmonic motion, at any the maximum velocity, the velocity will be represented by this function cos theta. So cos theta will come like this and it will cross like this. So and the maximum value of the velocity will be x0 omega. So from this thing, since you know the maximum value of velocity is x0 omega, and it is represented by a function that is cos omega t. So it can also be represented in the vector rotating vector diagram. So this is the rotating vector diagram for velocity. The amplitude is x0 omega and theta is the angle from the x-axis, and in this case you have x0 omega cos omega t. So theta is equal to omega t, that you know already. So in this case projection on the x-axis will be your required quantity, because this value, x-axis value, will be equal to x0 omega cos omega t. And if you want to keep the rotation same as what you use for displacement, that if you want to take the projection on the y-axis, then you you shift this diagram by 90 degrees. By shifting this diagram by 90 degrees, you will get this value as 90 minus theta, and hence since cos 90 minus theta is equal to sin theta, or the sin 90 minus theta is cos theta. So here in this identity you can have the expression for velocity is equal to x0 omega sin 90 minus omega t, and plus phi. Phi anyway constant, doesn't matter for the rotating frame of reference. So 90 minus theta, theta is equal to omega t. So this is the, so vector diagram is 90 degree shifted vector for velocity. Vector for velocity is 90 degree shifted to vector for displacement and has magnitude equal to x0 omega, that is amplitude for the displacement. But similarly, if you want to calculate the acceleration, then you differentiate the velocity, so it will be dv by dt, and d by dt of velocity we saw it is x0 omega cos omega t plus initial phase phi. So if you differentiate this expression, x0 will come out omega, differentiation of cos theta is minus sin theta minus sin omega t plus psi, and differentiation of this expression is omega. So you get omega square x0 minus omega square x0 sin omega t plus phi. So if you compare this expression with the expression for displacement, x is equal to x0 omega t plus psi, both are almost same except for the scaling factor of minus omega square. Hence acceleration is equal to minus omega square displacement. This is a property of simple harmonic motion. Now this the maximum value of acceleration is equal to maximum value of sine expression is 1, so maximum acceleration is equal to minus omega square x0, where x0 is amplitude of the vibration of the displacement, and omega is angular frequency. And if you want to see in the phase diagram, if this was your x vector, the v vector was 90 degrees shifted to the x, and the acceleration vector will be 180 degrees shifted. So the maximum value of this will be x0, this thing is omega x0, and this is omega square x0. And since this minus sign is coming, so that's why it is 180 degrees shifted from the x. This is initial phase xi, and all three are rotating at an angular velocity of omega. So this is rotating vector method. So like when I told you that you can add, you have multiple vibrations in the system, and if you want to add the displacement, you can do that. If you want to add the velocities, you can add the velocities by vectorial convention. Similarly, you can add the acceleration also. So by decomposing the vibration into vectors, it is much easier to handle those, and you can handle addition, subtraction, what kind of superimposition you want to do for the vibrations. So this same property allows us to decompose a very complicated vibration into simple harmonic components, because from the Fourier series you know that as any periodic motion can be decomposed into harmonic motion. So I'll write the final expressions or the equation for the harmonic motion. That this you should better memorize, because they will come handy if you already know the definition. So sine pi by 2 plus, it was cos omega t plus psi. So cos is sine pi by 2 plus psi. So we are following the same convention. We are using all sines. So it will be pi plus omega t. So pi plus omega t will be equal to minus sine. So then minus omega square x0 sine, this expression you will get minus omega square, and if you take the pi out. So from here you can see simply the space, this omega t plus I, this is pi by 2 plus omega t plus I, and pi plus omega t plus pi I. So the phase is this is pi by 2 shifted and this is pi shifted. Acceleration is pi shifted. Velocity is pi by 2 shifted from the displacement. We will now move on to derivation or the analytical derivation of various modes of vibration that we discussed in the introduction, that is free vibration, forced and damped vibration. But before doing that, we will lay down our basic vibration model. So what is the system that we are going to analyze? That will remain same for all the cases. So we will consider a typical vibration model of spring mass system. So this is just a representative, and the same theory can be extended to other models also. In the present case, the potential energy stored in the spring is the potential energy of the system, and the kinetic energy is of mass. So that is linear displacement. So this is the potential energy stored in the material and linear displacement system. Similarly, for any system that you consider, you can draw analogy to this system. You will have a, let's say, torsional pendulum. In the torsional pendulum, the torsion in the rod is analogous to potential energy of the spring, the strain in the spring, and the angular motion of the disc is equivalent to the linear displacement of the mass here. So similarly, for a simple pendulum or a machinery in vibration, let's say a cantilever beam, it is having the mean position, it is moved from the static mean position, it will have a vibration like this, up and down. So the cantilever beam, the angular displacement is analogous to linear displacement, and the strain energy stored in the material will be analogous to the potential energy of the spring. So similarly, for all the mechanical system, even the gravitational system, so like let's say there is a ball sitting on the crest and trough, and here the ball, this is a static position, equilibrium position of the ball, that is the position of least energy. But if you displace it some distance towards the right and leave it, it will keep on doing a simple harmonic motion about its extreme position. So the angular displacement of this motion will be analogous to linear displacement, and the gravitational energy will be analogous to potential energy in the spring, gravitational potential energy. So similarly for the simple pendulum also. So in all of the vibration model, you can draw parallels with the spring mass system. So hence we will do our analysis for the spring mass system, and the same results can be extended to other categories, other kind of vibrations. We'll assume some basic assumption related to the spring mass system, which will help us to derive the equation for linear oscillations. So the first assumption is that the spring is massless. There is no mass of the spring. So if the spring is massless, the force acting on the two ends. So at the bottom end some force is acting, the top end force is acting. If the spring were to have some mass, then the force at the top end would be different. It would be weight of the spring plus weight of the mass. So since the spring is massless, then in that case the force on both ends of spring will be same. The second assumption is that the expansion or extension of the spring follows linear Hooke's law. So what does the Hooke's law say? Hooke's law say that stress is proportional to strain, linear. So you can have a constant of proportionality, let's say K, that is called Young modulus for the material. So stress is K times strain. This is the linearity relationship. So if you extend the material too much, if you recall the material expansion diagram, the stress strain diagram. Uh, so this is strain, this is stress. So stress strain diagram, there is a portion of diagram where the linear relationship is obeyed, and after that the strain becomes high for a negligible, for a small increase in stress. So this is called non-linear regime. So we are not considering the non-linear regime. We are only considering the linear regime. So that's why our oscillations are called linear oscillations. So this this property is conserved if displacement is small. Displacement is small, then our oscillation will be linear oscillation. Will not go into non-linear stream. The first strain is small. So this is a second assumption for our derivation. We will not talk about the non-linear regime because that is a total different thing altogether, considering non-linear oscillation and deriving the expression for acceleration velocity of those. So this is beyond the scope of present studies. We will only consider linear regime. So for the spring, what does it mean? For the spring, you have a static position, static equilibrium position, and there is some initial extension in the spring, let's say L0. So this is the static position. If you are pulling the spring, then increase in length of the spring is proportional to force applied, so additional force applied. So, so this so if you are considering the displacement as x, then F will be proportional to F will be proportional to x, or F is equal to kx. There is a linear relationship between the both. So you have to apply kx amount of force to have x amount of displacement. So this is our basic law for the spring, and for different systems also you will find similar analogy. So similar analogy, analogous. Say in the torsion pendulum, the torque will be equal to some constant proportion into theta. In the like gravitational cases, like your simple pendulum or a ball on the curved surface, you will find that the acceleration or the force towards the mean position is a function of height, the displacement from the mean position. So this height will be important there. So this height will also can be expressed in the terms of theta, how much displacement has taken place. So F is equal to k theta. So similar analogy will get for all the cases. So this is our vibration model, that spring mass system, a mass attached to the spring hanging from the spring of the proportionality constant k. So F is equal to ks. This is our basic linear oscillation free system. So in this case, there are no losses. So it is a free vibration. The vibration will continue forever if there is no energy taken out from the system. But if you consider damping, then that thing is represented by the help of a dash pot, represented by a dash pot attached to the system. So in that case, the losses will be proportional to velocity. So I will just show you what a dash pot is. A dash pot is nothing like you have a pot, and then you have a rod coming inside and a piston, and there are some holes in the piston. So when this rod is moving down or up, any direction, when it is moving down, the fluid from this side will come to other side. So there will be pressure drop across the orifice, across small of orifices that are existing in the dashpot plate. In the dashpot plate, and this pressure drop is basically a loss of energy loss. So that energy has to be supplied from somewhere. That energy will be supplied from the force, the force which is pushing the piston down or pulling the piston up. So energy will be extracted from the source. Because this is an enclosed system, there is just a fluid inside this dashboard, and the fluid is moving from one side to another side when the dashboard plate is moving up and down, but there is no internal source of energy, so energy has to be extracted from the source. So in this case we will consider damping as equivalent to a dashpot. Let's say we make a notation like this and connect it to our mass m. So this is a representation of damping. So when a displacement of our object will take place, the piston inside the dashpot will also move, and then there will be losses. So it is found from the fluid dynamic derivation that the losses are proportional to velocity. Since in a flow across a orifice, if you have velocity v, so delta p will be proportional to v. So loss is proportional to velocity. So hence here adding this dash part will mean that we are exerting an extra force of damping, that is equal to some constant of proportionality, let's say c, into velocity. So velocity is x dash. So f damping will be equal to c into x dash, constant of proportionality. So when you draw the free body diagram of mass m, you will have a F due to the extension of the spring, that is kx, that we just saw in the linear displacement model, and then you have a damping force that is proportional to velocity. So it is having x displacement from the mean position. Let's say this is x equal to 0 position, and this is x displacement, and at any time instant it will have x dash velocity, and you will have x double dash acceleration. So the damping force at any point of time will be equal to the velocity multiplied by a constant of proportionality, that is called the damping constant. What about the direction of forces? So in the spring mass system, you have damper and spring attached. So let's say the zero position is this, x equal to 0, and the displacement is x from the 0 position at any time instant t. So I'm equal to t. So that since the displacement is towards the bottom from the mean position, so the spring force will be towards the top. It will try to come back to the equilibrium position, because the equilibrium position lies on the top of the real position. So spring force will be towards the top, and at the same location we have to determine the velocity. So let's say at this instant if the velocity is down, so this piece is getting pulled, and it will resist that thing. Any damping will resist the motion applied on it. So for determining the direction of force of the damping, you should keep in mind the basic law that any damping will resist the motion applied to it. So if the velocity direction is down at any time instance, then the damping force will be towards the top. If the velocity is towards top, let's say it has reached the extreme position and it has started coming up, that time in the same cycle the damping force will be down. So if you see the oscillation from 0 to extreme position, both FD and FS will be top. Then when it starts coming back to the mean position, towards the mean position, then the damping force will become towards the down, while the spring force still remains towards the top, although the magnitude is reduced. So hence they keep changing direction the time. This we have to consider during the derivation. You have to keep in mind But the only thing you have to keep in mind is that you take the displacement from the mean position and opposite that direction will be the spring force, and you take velocity at any time instance, the opposite direction of the velocity will be the damping force. So with this we have outlined a framework for our derivation. Now we will go on to the analytical derivation of free force and damped vibration of the system. So we will first take up the case of the free vibration. In this case there is no damping and there is no external force. So the diagram will look simple. There will be a spring mass system and there will be a static deflection due to the mass of the spring. So the mass of the spring mass system, the mass m, there will be static deflection. Let's say x static is equal to, that too you can get from your equation, that F is equal to kx. So the F is the static force in the system. The static force in the system will be equal to mass due to the weight due to gravity. So mg is the static force. So mg is equal to k into F static. So this will be the equation for static displacement. You can get the static deflection is equal to mg by k. So this is your equilibrium position, the zero position, and this will have a static deflection, predetermined deflection. However, for our derivation, the static deflection will not matter. We will just consider a static equilibrium position and will consider the displacement with respect to that static equilibrium position. So for us, the dynamic displacement, dynamic deflection is of importance for vibration. So let's say at time t, the spring mass system, this is a static equilibrium STEQ position, and at any time instance the deflection is x from the mean position. Then there will be tension in the spring and there will be a force in the spring. So that force can be given by F is equal to k into x. So the displacement from the mean position. However, the actual tension in spring will be equal to mg plus kx. F actual will be equal to mg plus kx, but this mg will get cancelled out, that you will see from the derivation. So if you consider a free body diagram of mass m, you will have F spring, the actual force in the spring, and downwards you have the weight mg acting. So net force on mass m will be equal to F spring with actual minus mg. So this will be equal to mg plus kx minus mg. So net force on the mass deflected from static position, the mass is deflected from static position by x, the net force is equal to kx. So the displacement, the dynamic deflection multiplied by the constant of proportionality of the spring. Now you know that acceleration can be mass into acceleration is equal to force. So what will be the nature of the acceleration here? So as you know that the force will be towards the top, F is equal to kx will be towards the top. So the acceleration will also be in the same direction. Acceleration of mass will be in the same direction. So let's say x double dash is the acceleration. So mass of the object is m into x double dash is equal to kx. However, here you have to pay attention to the sign convention. Now in this diagram you have seen that if this is a zero position and if x is considered positive downwards, so x is positive downwards. You can take the opposite also, but you have to be consistent in your convention. You cannot take two convention at times. So x is positive downwards, so x double dash will also be positive downwards. So but in this case the force is acting towards the top, and hence acceleration is towards the top side. So hence the acceleration is negative in this case. So that's why you put a minus sign here. So this is important from sign convention. Otherwise you will get completely different solution. So you have zero position here. This is x, x dash, x double dash. This is the positive side towards the bottom. If in the present case f is towards the top, because the displacement is from the zero position towards the bottom, hence the x is positive, but x double dash is towards the top, hence it is negative. From this we get our equation of free vibration, that is mx double dash plus kx is equal to 0. So we will go about solving this equation in the next slide.